Good morning, everyone, and welcome to the IBM Qiskit Live for the IBM Quantum Seminar Series, as we have now shortened the name, dedicated to you, the research and academic quantum communities. Now, in just a minute, I'll be thrilled to roll out this week's episode with Professor Marko Žnidarić from the University of Ljubljana, Slovenia. Before we get there, I'm so glad you joined us on time. And I see some of you already posting in the chat where you have tuned in from. So we'd love to begin our seminar with a tradition that gets us warmed up for the live interaction during the seminar, which is to write in the chat, where are you guys tuning in from today? So you can reply to that in the comment chat box located on YouTube, somewhere above, below, left or right, where you can let us know where you're coming in from today. Now, that's the same place where you can ask questions live of Marko and myself during the presentation, and we'd love to have a lively and interactive discussion and really keep this more of a discourse going. Now, this week, we have a very special new series on the channel that's featuring a quantum paper review. And the very first paper this series is on the quantum utility paper published in IBM, which showed us what we can do with 120 qubits, depth 60 circuits, 127 qubits, depth 60 circuits from the IBM team. And check it out. It's a real nice deep dive. Next week, we have a paper coming out on the review from myself and colleagues, Oles, Derek, and folks, as you will hear on the seminar soon, which will also talk about a very exciting many-body physics experiment that will tie into a little bit today of what you will hear about from Marko. So, folks, let me remind you before we dive right in that this seminar takes place every Friday at noon Eastern Time. The video will stay recorded, but you can only discuss and chat live during the series. So, to know what's coming up, click like and subscribe. It's time to get started. I'm your host, Zlatko Minev from IBM Quantum Research, and on this episode 141, where we have folks from Germany, Oregon, India, Yokohama, New York, and many more places, I have the delight and privilege to introduce you to Professor Marko Žnidarić from the University of Ljubljana, Slovenia. Hello, Marko.
Hi, Zlatko.
How are you today?
Fine, good, thank you.
Well, we're so glad you could join us here. Before we pull up your slides, allow me to introduce you briefly. Marko is a professor of physics at the University of Ljubljana, Slovenia. After obtaining his PhD in 2004 on the stability of quantum dynamics in logarithmic echoes, Marko became interested in quantum information and more broadly in the physics of quantum many-body systems. Marko then studied transport in spin chains, Lindblad master equation, one of my deep personal favorites and close to my chest and heart topics. And more recently, Marko came across an interesting effects in non-Hermiticity that just a few years ago he thought were just obscure mathematics. So with that, it is my absolute pleasure to turn it over to you, Marko. The stage is yours.
Thank you, Zlatko. Very happy to be here. Yes, so I will speak about some relatively recent discovery that we came across a couple of years ago. It deals with the spectra of non-Hermitian operator, and the behavior that you can get out of it is kind of interesting, and I hope you will also find it a bit amusing. So let me just start with a bit of a reminder that spectral properties of, say, linear operators or of matrices are, of course, pop up throughout physics in very many different fields. So, for instance, in quantum mechanics, if you look at spectra of atoms, then the spectral lines are given by the eigenenergy differences of the corresponding, say, Hamiltonian. And experimental observation of those spectra was actually one of the motivations to really come up with quantum mechanics. People observe this very regular structure of spectral lines, and then they try to come up, for instance, Borwick's model of an atom, and then quantum mechanics was the correct answer at the end. Phase transitions, for instance, is another case where eigenvalues and spectral properties matter. For instance, in a simple case, imagine that we are discussing zero temperature situation. then you know that at 0 temperature, the system will find itself in the ground state. And so then whether you have a phase transition or not depends how this ground state changes as you vary parameter, and you can have this discontinuity if you have degeneracy. Another case is quantum chaos. So chaos in general, like if you go to classical chaos, one way to define chaos is really through complexity of dynamics. So the system is chaotic if it, as you evolve it, generates a lot of information. In other words, if the information required to describe system up to some time grows exponentially in time, then you say, okay, system is chaotic. Now, in principle, you could say this, you could use the same criteria also for quantum systems. The problem is that it's not so easy because it's you have finite h bar, observers don't commute, and also in practice, even if you have a nice idea, in practice it's hard to calculate those quantities that measure complexity in time. So people have tried to come up with simpler, like theoretically perhaps not so elegant formulations, but easier to use in practice. And perhaps the most commonly used quantifier or criterion of quantum chaos now is so-called level spacing statistics. So level spacing statistics is just you have a quantum system, so some Hamiltonian, you can calculate eigenenergies, and then you look at distribution of the eigenenergy differences between two consecutive levels. And if you plot a histogram, you get the picture like shown there. And there is a marked difference between chaotic systems and extremely non-chaotic ones, which are the integrable systems. So integrable systems have this usually have this exponential distribution, which is called Poisson statistics, whereas chaotic systems, you can see in the picture, have distribution that looks this bell-shaped, and in particular you have very small probability of having two eigen levels very close by. So this is called level repulsion, and this is like one criteria of quantum chaos. And another, like fourth example is something not necessarily particular to physics. It's looking at Markovian processes. Actually, my example that I will give you of this strange non-Hermitian phenomena will involve some Markovian process. But here, just as to be a bit more generic, for instance, in computational science, if you want to know the speed of some algorithms, for instance, just to be concrete, let's suppose you want to solve a system of linear equations. So some matrix A acting on unknown vector X gives you some known vector B, and you would like to calculate X. Then there are very different methods how to do this numerically. For instance, you might have heard about Gauss-Seidel elimination method. Then there is SOR, successive over-relaxation, and so on. So those methods are often iterative. So basically, you are trying to approach with X closer and closer to the correct exact solution. And the way you can do this is you split your matrix A into two parts, M and N. And then the X approximation of the next step, which is supposed to be better, is obtained, given by this formula, which tells you that you have to multiply X on the previous step by matrix M to the power of -1 times N. And so now you will believe me that how fast you converge with this X to the correct solution depends on the spectral properties of this matrix M to the power of -1 times N. And in this case, actually, and this has been known in numerical mathematics for many years, actually, sometimes it happens that the spectrum of this matrix is not the correct thing to look at. So clearly, you will agree with me, I suppose, that spectra are important in very many different situations. Well, this talk is about a situation where actually spectrum of a matrix is irrelevant. To be more precise, I will speak about a situation where relying on a spectrum to give you some prediction will give an incorrect answer. And as we will see, such a thing can happen if you have non-Hermitian matrices. So in Hermitian matrices, everything is fine. Spectrum is really the correct object to look at. In non-Hermitian matrices, it will turn out, I will explain you have to look not at the spectrum, but at something which is called pseudospectrum. And I will explain you later on what exactly pseudospectrum is. Another alternative view at the problem that I want to discuss is sketched here at the bottom. So I mentioned phase transitions on the previous slide. Right? So phase transition in a nutshell is a phenomenon where a small change in some parameter gives a large effect. And such situations are of obvious interest, right? You have high controllability. Now let's just in 2 lines try to mathematically see under which circumstances can we have such a situation that small change leads to a large effect. So again, let's say we have some linear operator, a matrix if you want, A, and we write spectral decomposition of this matrix. So we express this matrix in terms of eigenvalues lambda j and left and right eigenvectors. Right eigenvectors are rj, left eigenvectors are lj. And I'm deliberately keeping distinction between the two. For Hermitian operators, left are equal to the right, but for non-Hermitians, this is not the case. And so now, if we perturb this matrix A by some matrix V with strength small epsilon, then everyone knows first order perturbation theory tells you, for instance, that right eigenvectors change is given by this equation, right? So it's sum over all k is not equal to j of matrix element divided by the eigenvalue difference. So now if we look at the relative change of this eigenvector, then you can estimate this relative change is equal to epsilon times sum of those fractions. And fraction is in the numerator, you have a product of norms of left times the right eigenvector divided by the eigenvalue difference. And so now if we want a large, to have large effect, right, then these fractions have to be large. And there are 2 ways to have that. One way is that you have degeneracy, so that the difference between lambda j minus lambda k goes to 0. And this is what is traditionally studied in physics in very many different situations, right? And that's fine, right? Because for Hermitian systems, left eigenvectors are equal to the right eigenvectors, and they are also normalizable. So norm of left is equal to the norm of right eigenvector, and this is 1. Yeah? But in non-Hermitian systems, non-Hermitian matrices, it can happen that the product of those norms can also diverge. And so you have another possibility how such large effects can happen, namely that the norms of those eigenvectors diverge. And so my talk will be about situations where that can happen, where that happens. Okay, so it's non-Hermitian matrices. I mentioned them several times so far already. We know, of course, that quantum mechanics is unitary, generator is Hermitian. So how can we get non-Hermiticity? Well, imagine a many-body system. So Hilbert space in a many-body system is very large. It's exponentially large in the number of qubits that you have. And so you will never be able really to control the full exponentially large Hilbert space or measure all possible observers. So the relevant dynamics is always some reduction from this exponentially large Hilbert space to some subset. And so if you do this either formally tracing out some degrees of freedom, or if you do some coarse graining, as perhaps in statistical mechanics would be the way to go, you will typically get some non-unitary evolution, and therefore it will involve some non-Hermitian matrices. And so here's the setting that I will focus on. I will try to understand because I aim aim for some analytical understanding. I will try to consider as simple a situation as possible. So I will try to understand the relaxation process. So imagine that we have the following setting. So we start with some pure product initial state, psi 0, and then we evolve it with some unitary propagator u for time t. And if this unitary is really sufficiently complex, say quantum chaotic, then we know that after a long time, we will completely thermalize. So the final state psi of t after a long time will be very similar to a random state. And properties of a random state we know very well. We can calculate anything you ask for a random state. What I would like to understand here is this process. How do we get from this initial product state, some very simple looking state, to the final one? In particular, I would like to understand whether this relaxation process is, for instance, uniform, just simple exponential decay, or can you have something more complicated? And just to make things even simpler, I will not look at the whole evolution in the Hilbert space. I would look at some scalar observable. And the observable I will focus on in my talk will be so-called purity. Purity I of t is just trace of the reduced density operator squared. So in such situation where the whole evolution is pure, so state is pure at every time, this purity is just one measure of entanglement. So if you start with a product state, purity will be initially 1. So this is the maximal possible value of purity. Then it will gradually decay. The larger bipartite entanglement you have with between subsystem A and its complement, the smaller is purity. But the same phenomenology is also observed in other observables. One would be so-called out-of-time ordered correlation function, OTOC. I'll just briefly mention them towards the end. Okay, so what is now exactly? Let's get really concrete. So what is exactly the phenomenon that I'm trying to describe? The setting that I will discuss will be when U, the propagator, is a random circuit. I will show you on the next slides how this simplifies analytical treatment. But the result will be that in this case, the evolution of purity is really Markovian. So you can write purity at later time, say at time step t plus 1, is obtained simply by multiplying your previous vector of purities with some matrix M. And when I say a vector of purities, I mean that just you can calculate purity for different B partitions. And if you have n qubits in 1D, you have 2 to the power of n different B partitions, because each qubit can be either in A or its complement. And so I just pack all these 2 to the power of n different B partitions, purities for different B partitions, into a vector of I. It turns out that you have this nice Markovian evolution. And so this Markovian matrix has now a spectrum. It's diagonalizable, so there are no problems with that. The largest eigenvalue is equal to 1, and then there is the second largest in modulus, say lambda 2, and then there are smaller ones. Lambda 2 is always gapped away from 1, so it's a finite gap, finite difference between 1 and lambda 2. And so the standard folklore would now tell you that, and the eigenvalue 1, the corresponding eigenvector, corresponds to a steady state. This is just purity of a random state, so this is a asymptotic random state. So now I would like to understand how fast I converge to this asymptotic random state, right? And so what I will look at throughout my talk is at purity at time t minus purity at infinite time. And so standard folklore would now tell you, well, yeah, for long enough times, asymptotically in time, these smaller eigenvalues, lambda 3, lambda 4, and so on, to the power of t will be very small, negligible compared to lambda 2 to the power of t. And so you should see asymptotically decay as lambda 2 to the power of t. Yeah, this is what we thought. Okay, then we did numerics like 3 years ago. And this plot shows what are the results. So what we are showing here on y-axis in semi-log scale is just some observable. Here actually is OTOC, not purity, but purity would look the same. Versus time for 2 different system sizes, 20 qubits and 34 qubits. So if we just focus on 34 qubits for now, this is blue points, then you also see a green dashed line. So green dashed line is lambda 2. We can calculate lambda, the second largest eigenvalue, analytically, and can plot how this looks like. It's just exponential decay with this green slope. And if you look at blue points now, you will see that from time around 15 onwards, indeed, you decay as lambda 2 to the power of t, as expected. So everything is fine for long times. But if you now compare 20 versus 34 qubits, you will see that this transition point between this asymptotic decay it moves to longer and longer times as you increase system size. And so now if you take thermodynamic limit, correct thermodynamic limit is first system size to infinity and only then time to infinity. For instance, if you want to look at long times, when you send n number of qubits to infinity, this transition time will be pushed to infinity. So the decay that you will observe will be actually the initial phase where the rate of decay is different. It's not given by lambda 2. And so the finding is, well, apparently not always. The second largest eigenvalue doesn't always give you a correct asymptotic decay rate. At that time, we didn't yet understand where this slower decay rate comes from, because you see, it was kind of mysterious. So we call this phantom relaxation and phantom eigenvalue for the following reason. On the right plot, what is sketched here is how the spectrum looks like of this matrix M. So there is this eigenvalue 1. You can see it on the real axis on the right-hand side. And then it happens that in this special case, all eigenvalues are actually real. So these are those crosses and red line on the x-axis. And the largest one, lambda 2, is marked there. Whereas this phantom relaxation, this mysterious initial relaxation up to time 15, is marked lambda phantom there. So it looks as if there would be, larger eigenvalue than lambda 2 in the spectrum, even though there is no. So there is like a ghost, a mysterious eigenvalue that somehow nevertheless determines the decay rate. And I will explain you how all this comes about. Okay, so here is a brief sketch. First, I will introduce, say, a few words about random circuits, and then I will focus on this purity. In random circuits, where we will have this Markovian description, and we will have this two-step decay, and then in one exactly solvable case, I will be able to show you some details.
And maybe you're about to get into this, Marco, but one clarification was just, when you say random circuit, do you mean random as in random matrices, or you're randomly picking gates, or you have a fixed brickwork circuit and you're randomly picking angles? Like, which kind of random circuit?
Right. This is exactly my next slide. So excellent question, just on time, So let's just proceed to my next slide. So random circuit is just a circuit composed of random gates. In my setting, just to fix a unit of time, within unit of time, I will always apply 2-qubit gates between all nearest neighbor qubits. But I will vary between different geometries. So either like a brick wall, which is this frame A, or frame B shows what is called a staircase configuration. And now going to your question, Zlatko. So random gate now mean that each 2-qubit gate has some randomness, and I will discuss 2 cases, because those 2 cases I can treat analytically. At the end, I will actually comment about other choices. Essentially, the result is that you will get the same physics, only you don't have any analytical solutions in those cases. But the 2 settings are either the 2-qubit gate is fully random Haar, so completely random 2-qubit unitary, for the experts Haar distribution, or I can also treat case where I pick a fixed 2-qubit gate, like say control node gate, plus random single qubit unitaries. So single qubit unitaries is enough. Again, single qubit unitaries is like Haar distributed, so if you write this in terms of some angle, it's random uniform on a Bloch sphere, say.
Mm-hmm. Mm-hmm. And maybe the motivation for the brickwork is more clear and obvious, since that's how a lot of Trotter circuits look. But can you tell us the motivation for the staircase example?
Yes. For this solvable case that I will discuss, actually staircase is the interesting case. But to continue, it's not always that you have this. So this phantom relaxation you can get for different circuits. So for instance, if I would focus on the AUTOX, out of time ordered correlation functions, then actually for the brickwork I would have the effect, but for the staircase I would not. So it's kind of depends on the observable that you look at. Yeah, but the motivation was basically staircase was the just a different, simple looking setting. That's why we studied it, and in fact it turned out that it's kind of interesting.
Mm-hmm. Mm-hmm. Okay. All right. Thank you.
Yeah, so just a few historical remarks perhaps about random circuits. Um, it's not just of theoretical interest. People do also experiments with random circuits. I'm here highlighting just two. One which is one of the earliest ones that I'm aware of. This is this Emerson and collaborators from 2003. So early days of quantum computation. Among some numerics in that paper, they also did experiments on 3 qubits. Yeah, so very different than today. This was in the context of quantum chaos. Basically, the question was, can you simulate dynamics of quantum chaotic systems using random circuits? And the answer was yes. So those were the days, some of you might remember, where like I think 2 years earlier, IBM famously factorized number 15, showing that it's 3 times 5 on a 7 qubit quantum computer. This is the middle picture that you can see there. So this was all liquid NMR. And the right-hand side picture is more recent ones from Google AI and their supremacy paper, where of course you have now much more qubits, much more controllability and so on. But in both cases, it was random circuits that people studied, not exactly of the type that I'm considering, but say almost the same. And more recently, there is another sort of theoretical twist why people are interested in random circuits. Is basically because they can serve as a simple proxy, often solvable case of many body dynamics, and then you can study operator dynamics and questions going beyond just entanglement, like purity in my case. All right, just to perhaps 2 sentences of how you get this Markovian description and to give you a bit of a flavor how it looks like end of the day. So we have these random gates, either 2 qubit random or just single qubit random unitaries. And after you do averaging over those Haar random gates, it turns out that purity is described as this simple Markovian process. This was first observed by Oliveira and company in 2007. And there was also a very nice recent paper from 2020 by Yi Zhuangyou and collaborators. And I'm using basically their formulation. And in their formulation, you basically pack all the purities for all different bipartitions, this vector of purities, and then you have this simple iteration. So for instance, vector of purities after t steps, after time t, is just m matrix m to the power of t acting on the initial vector. So this matrix is exponentially large, so it's still like a very complicated problem. It's of size 2 to the power of n times 2 to the power of n. And but the structure is kind of in a way simple. Basically, what you have to calculate is just corresponding two-side Markovian matrix Mij. And for instance, for this simple case where I pick 2 qubit gate to be a fixed xy gate plus just single qubit unitaries on each wire, on each qubit, this matrix is this simple 4x4. It's real, symmetric, so very nice looking. So this is like two-side matrix corresponding to application of a single gate. And now if you have a circuit composed of many gates, for instance, this staircase with open boundaries, you just have to multiply those two-side amps in the same order as you apply the gates. And important to note here is that a product of symmetric matrices is not necessarily symmetric anymore. And this will play a role, right? Because for Hermitian matrices, there are no surprises. For non-Hermitian ones, you can have these fancy effects that I will now go on to describe it more in detail. All right, so we have this Markovian description, good. So matrix M has, as I said, one eigenvalue 1. This corresponds to infinite time, so random state. You know what this steady state is. And there is, for those random circuits that I described you, the gap is always finite. And we did some numerics with my PhD student Yash Bensa, and we observed this surprising behavior that up to some extensively long times, so up to times that are proportional to the n, to number of qubits, decay was actually different. So it was slower. S if there would be some mysterious phantom eigenvalue. So bottom line is decay rate is not always determined by lambda 2. And there have been several sort of, now we understand, observation that can be related to the same underlying mathematical properties. Namely, in open systems, in some situation, you can describe everything by a very simple master equation, which is called Lindblad master equation, written down there. So there is some generator of this Lindblad evolution, this script L, which is also non-Hermitian because the system is open. And so the spectrum of this non-Hermitian script L generator always has one eigenvalue 0. The corresponding eigenvector is just the steady state. And then often there is a finite gap. But even if the gap is not finite in thermodynamic limit, still you would expect that the relaxation rate would be given by this gap. The difference between the eigenvalue 0 and then the smallest one in absolute value. So I actually made some numerical observation about that some years ago already, but more recently Takashi Mori and Shirai took it again, the same problem, and actually realized why this mysterious observation happened. Namely, indeed, there are situations where the gap does not give you relaxation rate. And it's connected with the same mathematics that I will now go explain in next slides. Okay, so how can that be, right? So, I mean, why is it that the largest non-trivial eigenvalue, lambda 2, doesn't give you correctly relaxation rate? Okay, so again, spectral decomposition, you already know that. M. Important point and crucial point is that for non-Hermitian matrices, operators M, Lj are not orthogonal anymore. They still span the whole space, but they don't form orthogonal bases. And the same holds for right eigenvectors. So you still have B orthogonality. So inner product between Rj and Lk is delta Jk. So 1 if you have the same index, but Ls are not orthogonal nor are right eigenvectors. So what does that mean then? Okay, let's now evolve with this M some initial vector, I at time 0. Then what you get in your spectral decomposition is expansion coefficients, Cj, which is just the projection of your initial vector, I at time 0, on left eigenvectors, Lj. Now, if Lj's are not orthogonal anymore, then this expansion coefficient is not bounded anymore by the norm, the length of your initial vector. So, simple example, say you are in two dimensions and your two vectors L1 and L2 are almost collinear, so they just point in one direction. And now if you want to expand some initial vector which is almost orthogonal to these two guys, then it's clear that two expansion coefficients will have to be very large in order to almost cancel and then give you this orthogonal component. Fine. But now in a many-body system where you have some parameter, the size of this matrix, determined, say, by the number of qubits, n in our case, it can happen that actually as you increase n, this expansion coefficients gets larger and larger. They can get exponentially large. And so it's really that these very large expansion coefficients now can mask the role of eigenvalues up to larger and larger times. And if this time when asymptotic lambda 2 decay really kicks in, I'm denoting this by Tc, if this time goes to infinity in thermodynamic limit as you increase system size, then you have a situation where the limits system size to infinity and T to infinity don't commute. And because you have to take the limit n to infinity first, it's really this first regime up to time Tc which is the relevant, which in principle is like transient regime, but this is the relevant in thermodynamic limit. So for this relevant regime, then it's really eigenvalues and in a way irrelevant. It's this delicate cancellation between exponentially large terms, which must alternate in sign, and then at the end you can get decay which is not determined by lambda 2. So this is like a short mathematical explanation how this can come about. And now let us have a look at some one solvable case when we can understand in all the details how those spectral expansion works. And this is the case where we take 2-qubit gate to be really 2-qubit Haar random, so like maximally random. And on top of it, we take this staircase configuration sketched down there in the figure with open boundaries. Now, the reason to take this staircase configuration is that in this case, the problem can be simplified. Namely, if you are interested only in B partition in a subset of all to the power of n different B partitions, namely in those B partitions where you take first k qubits in a subsystem A and the rest in the complement, namely you just take B partitions with consecutive qubits, right? There are n such different B partitions. Then it turns out that for this simple staircase configuration, you have a closed evolution of those n contiguous B partitions. And so you can reduce the problem from, speaking about spectral properties of this exponentially large matrix to spectral properties of a matrix of size n by n. And so there is this smaller matrix. The relevant matrix is, I denoted it T. It's written at the bottom of the slide. So it has very simple form. It is just a Toeplitz matrix. So Toeplitz matrices, for those who might not have heard, are matrices where elements are the same along all the diagonals. In this particular case, on the diagonal, I have alpha square. In the first super diagonal, so one above the main diagonal, there are alphas. Above that, it's all 0. Whereas below the diagonal, I have increasing powers of alpha. So first line below the diagonal, alpha 3, then alpha to the 4th power, and so on. Where alpha is, I haven't mentioned. If you look at the top of the page, there I write this two-side transformation matrix M, and there is parameter alpha, which is given in terms of local Hilbert space. So this small d is just the local Hilbert space dimension, which would be 2 for qubits, 3 for qubits, and so on. So you can, with the same framework, we will deal with all qubits in this staircase open boundaries configuration. Now, whenever you stumble upon Toeplitz matrix, you are in the business because mathematicians know a whole lot of things about Toeplitz matrices. And in this case, actually, it was even nicer. So for this particular matrix, I could get all the eigenvalues, all left and right eigenvectors. So let me just briefly show you what are the results without going into any details. So on the top left figure, you again see how purity decays. So there is again like a two-step phases, but the difference in the slopes before TC and after TC is not very large here. That's why in the inset, I just plot local slope, which goes from initially, for short times, from this phantom relaxation rate towards lambda 2 at sufficiently log times. And the second figure below, frame B, shows the same now for different B partitions. K is just B partition. So for instance, K2 means that I have 2 qubits in a subsystem A, and in this case, I guess N was 100, so 98 in the rest. Whereas the green curve, for instance, it's 50-50, so half qubits, first half of qubits in subsystem A and the rest in its complement. And you can see that indeed you go from this phantom relaxation towards lambda 2. There is some non-negligible transition regime, right? So I will also be able to describe this transition regime. And now there are several different ways how you can calculate this phantom eigenvalue, actually. In this case, you can, in a way, forget this Toeplitz matrix itself. You can just write a recursive scheme how these n purities are evolved. And you can actually solve this recursion in the leading order in system size n. And you get the following expression that I wrote at the bottom, so you get just very simple expression how phantom eigenvalue depends on this local dimension. So for instance, the 2 qubits, it's 2 divided by 3, right? And I also have the full spectrum, so lambda 2, I also have exact expression. This lambda 2 is always smaller than lambda phantom. So initial decay here is always slower. But you can also get the same kind of result doing full spectral decomposition. So because for this simple Toeplitz matrix, I also have explicit expression for all left and right eigenvectors. And it turns out they are localized. So this is sketched at top right corner. In particular, left eigenvectors are localized at the right edge with some fixed localization length that depends only on alpha, local Hilbert space size, and not on the system size. Whereas the left eigenvectors or right are localized at the other edge. And so kind of because overlaps of those two guys is exponentially small in system length, right? This then means that if you enforce this b-orthonormality, then one of the two sets, either left eigenvectors or right eigenvectors, their norm will have to be exponentially large. And this effect of localized eigenvectors is called, in some more condensed matter context, non-Hermitian skin effect. And then you can also write these expansion coefficients. This is lower plot where, for instance, focusing on red triangles. So these are now expansion coefficients for all non-zero eigenvalues here, going from 1 to 19 in ordered form. So the largest eigenvalue here is actually index 1. And you can see that actually expansion coefficient corresponding to the largest eigenvalue is the smallest. So the largest expansion coefficient is actually the one corresponding to the smallest eigenvalue. And because y, left-hand axis, is logarithmic, you can see that it's many orders of magnitude larger, like 10 to 50 versus 10 to 10. So it's really not correct to say, okay, I will just neglect small eigenvalues, right? No, you have to take all, because you have these exponentially large coefficients, they alternate in sign and then therefore cancel each other. You can actually go to more details. I will not tell you anything of this mathematics. It's actually very nice. So there are some kind of magic, well, some trigonometric sums with magic properties are involved. Magic in a sense that for certain indices, the sum is mysteriously zero. For other indices, it's non-zero. You can describe the transition between the two regimes in terms of Jacobi theta functions. Theta functions are, in a way, generalizations of geometrical sum, and they have very nice structure in a complex plane. This is this rainbow, nice looking picture. But end of the day, what you get out of it, that indeed this mysterious phantom eigenvalue pops out of the overlaps between your initial vector of purities, which is a vector that has all elements equal to 1, because we start with the fully product state. So purities for all B partitions are 1, with the left eigenvectors. So you can say that this mysterious phantom decay is not visible anywhere in the spectrum. It's somehow hidden in eigenvectors. Now the matrix T or A, it's actually kind of interesting because it turns out that this is matrix of size n by n, remember? And then you have only n over 2 non-zero eigenvalues. So basically half of those, the size, is filled by kernel. So eigenvalue 0 is degenerate. It has degeneracy n over 2. And it's composed of a single Jordan block. Now, to describe this phantom decay for sufficiently long times, you don't really need to worry about this kernel and Jordan block. But also, there's some interesting mathematics in this Jordan structure. Namely, if you write this structure in terms of what is called generalized vectors or generalized Jordan vectors, then those vectors are also localized. And also in their structure, you can also extract this phantom relaxation rate. So in a way, this very simple matrix A or T is like this phantom relaxation rate, lambda phantom, is hidden in both, like in eigenvectors corresponding to non-zero eigenvalues, but as well as and independently in this Jordan structure of the kernel. So it's kind of very nice structure. All right, but still, now you might ask, okay, very well, for this solver case, you managed to calculate this phantom relaxation rate, but how about if you don't have solver case? How do you then get the correct relaxation rate? Because we have other cases, non-solvable ones, where we also observe the same phenomenon. Clearly, spectrum is not the correct object. All right, hint about what is the correct object to look at comes from the solver case. Namely, in this solver case, now you can imagine, okay, you increase the size of those matrices, go to thermodynamic limit, and then in the limit when the size of that matrix will be infinite, you get something which would be called an operator. I denoted it by T infinity. And now for Toeplitz operators, mathematicians will tell you what is their spectrum. Yeah, namely the spectrum of a Toeplitz operator, T infinity, is given by something which is called a symbol of a Toeplitz operator. Symbol of a Toeplitz operator is nothing but the Fourier transformation across the skewed diagonal of those, sizes of matrix elements along different diagonals. In the language of a physicist, this will be called like a Bloch vector. So this Z, complex Z, is like a K momentum for a physicist. And so if you evaluate now this symbol at the unit circle, this is what gets you spectrum of an operator, like infinitely sized matrix if you want. And so that spectrum is now sketched on the lower right-hand side. A red line and those crosses is spectrum for either a finite matrix crosses, or for very large matrix you just fill this line on the real axis. So therefore spectrum of every finite matrix lies in this red interval. In particular, lambda 2 is this 9/25. Okay, if you plot spectrum of the symbol, you get this oval shaped, egg-shaped circle. So you see, spectrum of an operator, like infinitely sized matrix, is completely different than the spectrum of every finite matrix. So we are dealing with a situation where spectrum is completely discontinuous in thermodynamic limit. And now if we, on that plot, also plot the value of this phantom eigenvalue, which we know because we were able to exactly solve everything, we get this 3/7. And so you will notice the 3/7 just touches the spectrum of the operator. So this mysterious phantom eigenvalue is nothing but the spectrum of an operator, like infinitely sized matrix. And so the catch was that we were dealing with matrices where spectrum for every finitely sized matrix was completely different than spectrum of infinite operator. Okay, good. That's fine. Some progress, right? But now, again, we were able to calculate the spectrum of T infinity, the correct operator in the thermodynamic limit, only because we had this simple Toeplitz form. If we don't have, then also we are not able to calculate the norm of T infinity. But there is another way, nice way, and that is you just look at mathematics books, and there is a very nice book by Trefet and Embry about something which is called pseudospectrum. So what is a pseudospectrum? So namely, it turns out that this spectrum of an operator is actually equal to a pseudospectrum of a finite matrix, finite but sufficiently large matrix. So what is a pseudospectrum? There are several equivalent definitions. I'm listing here 3. And they are defined in terms of some small parameter epsilon. Now, if you send n, the size of your matrices, to infinity, then the size, the value of this epsilon actually doesn't matter. So everything becomes epsilon independent. And so pseudospectrum, so point Z in a complex plane is in a pseudospectrum if the resolvent at that point is sufficiently large. meaning that in a way Z is almost an eigenvalue, not quite exactly, but almost, yeah, because the resolvent is very large. Alternative definition is that singular value, the smallest singular value, is very small, which again means that you are almost singular, right? Or the third definition, which is the one that is perhaps most useful for what I will show you next, is the following. So Z is in the pseudo spectrum if it is in the spectrum of slightly perturbed matrix for some perturbation E. So you just take your matrix T, and this gives us just a recipe how to in practice calculate pseudo spectrum of matrix, like very quickly and dirty. So you take your matrix T, some small epsilon, say 10 to minus 15, and just times some matrix E, say of random Gaussian numbers of variance 1. And you calculate this numerically diagonalized. And this is shown in the Minev plot on the bottom row. So what is shown here is I pick this 10 to minus 15 and then just diagonalize one instance of E. Yeah, just pick some E. Now for size 20, you see that these numerically obtained eigenvalues are almost the same as the correct exact eigenvalues except around 0. But as I increase system size to 100 or 500, that for 500, this numerically obtained spectrum is actually very close to the spectrum of the operator T infinity, to this oval shape. Yeah, because as I said, if you send n to infinity, using this small perturbation, you will actually get the pseudo spectrum, which gives you correctly this lambda phantom, remember. And so we have situation where, if you are very good and you are able to calculate spectrum of your operator exactly analytically, yeah, then you get these red points on the real axis with lambda 2 equal to 9 over 25 in this case, which is wrong. It doesn't give you a correct relaxation rate. If you are a poor soul who has to do numerics, yeah, you do this on a computer, there is some floating point rounding errors. If you use double precision, this is like 10 to minus 16, right? So you always are actually doing this sloppy numerical calculation. And then if your matrix is sufficiently large, actually what you calculate is not what you get out of it. These numerical eigenvalues will not be really eigenvalues. They will be these pseudo eigenvalues corresponding to the pseudo spectrum. And you will get the correct estimate for lambda phantom. So this is one situation where, a bit amusingly, if you are a bit wrong, like sloppy in your calculation, then actually you get the correct result at the end. There is also some interesting effect with this kernel, which I don't want to go much into detail. Let me just say that because this kernel is highly degenerate, right? The degeneracy of this kernel is n over 2. It is under perturbation. This degeneracy is removed very quickly. You have something which is called, you might remember from your math course, Poisson series. So dependence of these perturbed eigenvalues on the perturbation strength is not linear as it is for non-degenerate eigenvalues, but you have this high root dependence, like epsilon to the power of 1 over p, where p degeneracy. So the result of all this is that if you now ask yourself, okay, how large a matrix do I really have to take in order to be closer to this pseudo spectrum limit rather than the spectrum, which is the wrong thing, right? The answer is required epsilon is exponentially small in n. Yeah, so this transition from the spectrum to pseudo spectrum for this particular matrix happens exponentially fast in perturbation strength. Okay, let me just say that the safe phenomenon that I described you for purity and for this nice random evolution is also observed if you don't have any randomness. So for instance, you can even observe it in some Fouquet system, just some non-random gate, and then you repeat the same gate everywhere. And sometimes you also find this phantom relaxation. You find it also in other measures, so not just purity, higher Renier entropies. There's also a very nice recent paper just this week on arXiv by Shirin Jonai and Tianqi Zhou, where they have nice more physical picture in terms of membrane tension. So if there are any experts on random circuits, then you will know what this membrane picture is. So you can derive many results. So have a look at that paper if you want to know the details. And you also observe it in, as I said, auto out-of-time ordered correlation functions. So just as a final slide, let me just make some comments now on the pseudospectrum, because like take-home message is, if you're dealing with non-Hermitian matrices, then sometimes it can happen that lambda 2 is not the second largest eigenvalue is not the correct thing, right? So the message is, don't look at spectra, look at the pseudospectrum. And if pseudospectrum is different than spectrum, for normal matrices, in particular for Hermitian matrices, pseudospectrum is always the same as spectrum. But for non-Hermitian ones, the two can be different. Anyway, when we discovered that, we wondered, okay, very nice. So we discovered something completely new, right? And then you look throughout the literature whether there are any other instances in physics where people stumbled upon those pseudospectra. And of course, you find some. There are not many, but there are some. And actually, I will just mention two that are like kind of very nice application of this pseudospectra. One is from hydrodynamics. So everyone knows about turbulence, how hard this problem is, that it's sort of one of the unsolved theoretical questions, right? One of the unsolved questions might be, take some simple flow, I don't know, pipe flow in a circular pipe, or flow between two planes where you have some pressure difference. And then you might ask yourself, at what Reynolds number do I get transition to turbulence? Now, of course, people have studied that a lot. And you can get a rough estimate what is this critical Reynolds number by analyzing stability of laminar flow. At low Reynolds number, we know what is the flow, this simple laminar flow. And now you can look at small perturbation around this laminar flow. So you have some linearized linear operator. And then the eigenvalues of this linearized operator determine whether these small perturbations grow in time, if eigenvalues are larger than 1 in modulus, or whether they decay in time, right? And people have done that. And for instance, for plane Poisson flow, you get out of this linear stability analysis that Reynolds number should be around 6,000 for the transition. Then you go to a lab and do as careful experiments as you can do, right? And then experimentally you find that the transition happens at much lower Reynolds number, like 1,000. So it was mystery, where is this discrepancy? And actually, one of the reasons, say, important point to make here is that the linearized operator that you analyzed is actually non-normal. So it's like non-Hermitian. So you should not actually look at eigenvalues, but at these pseudospectra and pseudo-eigenvalues. And if you do that, actually you do get a hint that transition indeed should be expected at much lower Reynolds number, because you have this high sensitivity of eigenvalues. And then, okay, there are some two other cases. One is this non-Hermitian skin effect. Perhaps I don't want to go too much into details. There are also some long transient boundary modes in some bosonic Lindbladians observed by Lorenza Viola some years ago with her group. And there is this nice case that I will mention it. It's not physics, it's from card shuffling. Everyone knows. There is one way of shuffling cards, which is called riffle shuffling. You just split your deck of cards in two, and then you just randomly mix them like this guy is doing. And then you might ask yourself, okay, how many of these shuffles do I have to make to really randomize initially ordered deck of cards? And the answer is, for a deck of 52 cards, it's 7. So if you do less than 7, then you are very far from being random. If you do more than 7, then you are very close to being random. And actually, in thermodynamic limit, in this setting, thermodynamic limit means number of cards n goes to infinity, right? So 52 is not yet infinite. But in thermodynamic limit, this transition is actually discontinuous. So this is called a cutoff phenomenon in Markov chains business. And the corresponding Markovian matrix, again, it's non-symmetric. And if you calculate spectrum and compare it to pseudospectrum, you actually again see that they are different. And this is sketched on the right-hand side at the bottom. spectrum of the corresponding matrix are these points along the real axis, whereas pseudo-spectrum are these oval-looking shapes. And so here is my summary. I'm just mentioning here 2 papers that deal with this exactly solvable case. You can find also references to some other more numerical works. Take-home message is, if you are dealing with non-Hermitian matrices, beware, be careful about using lambda 2 and the gap to make conclusions about the relaxation rates. Sometimes it can happen, I'm not saying that it happens always, it can happen that true correct relaxation rate will be either slower or faster than the one given by the lambda 2. This comes because the limits n to infinity and time to infinity don't commute. This is actually very often the case in different settings. And the object that you should look at is this pseudo-spectrum. And there is this nice book by Trifetin where you can find more information. So I will stop here and happy to take any questions.
Thank you, Marco, for the wonderful talk and for clearing up the folklore a little bit in the many-body world. Folks, this is a great time to post your final questions as we come right over the hour here. So please do that, and I'll bring them up to Marco. Maybe just to start with some basic clarification. Let's say, suppose that in these vectors you looked at, say, the purity, and you looked at all 2 to the n. What would happen if you only looked at, say, a reduced version where you only looked at single site and 2 site, for instance, but you didn't think of all the partitions? Would you?
Right. So if you would have a still bipartition, right? A bipartition, so taking okay, 1 site is special, yeah. But already for 2 sites, if I take my bipartition to have just 2 sites and the rest, then still the phenomenology is the same. You can also study partitions where you have more cuts, more boundaries between subsystem A and A complement, right? Then actually what happens that, for instance, if I would take, like a B partition, what I would take middle 1/3 of qubits to be subsystem A, right? Then I have like 2 boundaries with respect to the complement, and then actually the K would be equal to phantom eigenvalue squared. So there is very simple rule how to get the decay rate for this completely hard random situation. For other cases, it's more complicated, and there we don't know exactly.
That's very interesting. Okay, so it sounds like basically even if you have these more, let's say, experimentally relevant measures and quantities, then you would potentially be able to move in that direction and see.
Autok would be like, if you ask me about experiments, I would start to think more about Autok actually rather than purity. And in this recent paper that I mentioned here by Shirin and Jianqi, they also find and argue that you will see the same phenomena also in simpler correlation function, actually. This like 2-step relaxation with different rates. So this is actually like very interesting from experimental point of view.
This is great. Do they always bend this way, or do they sometimes
No,
bend?
both ways. Yeah, you can have either faster or slower. So like here, these 2 pictures. So on the left-hand side, this is what we would call phantom decay, right? Because this initial decay is like slower. It's like in this gap, whereas the second one is initially faster, actually. But it's not faster in this trivial way that you would be orthogonal to all eigenvalues, right? Until some smaller one. It's again for the same reason that somehow you get these large expansion coefficients and cancellation.
That's interesting. Makes me really think back to some data on this. I mentioned at the beginning of the seminar we have a paper review on a paper from our team in 2 weeks, and there's a plot that looks just like this.
Oh, okay.
To the case and bends like this. So
okay, very interesting.
I don't understand why it happens like that, but maybe it's the same thing.
Of course, experimentally one has to say, right? Because probably in experiments, I mean, it's actually like having not being in the thermodynamic limit, n to infinity there, it's actually good. Because as you increase system size, this transition point goes to longer and longer time, and it will also happen at lower and lower values of either purity or Autok, right? So it will be hard to see. So actually, in this sense, I guess experimentally, you should pick like a not too large n, I would assume, right? Because you will not be able to measure very small values.
Excellent. And question from Shashi Kumar. Can you clarify the high kappa leading to spectral amplification, and basically how have folks reacted in the community when hearing about these effects and about non-hermiticity and the sloppy method?
Yeah. All right. So this spectral amplification. Yeah. Let me comment what I meant there. So you can also understand this. Say. Let's look here at the middle plot at the in the bottom row, right, where we have this spectra of perturbed matrices. So here, apparently, those unperturbed eigenvalues, true correct eigenvalues of my finite matrix T, must have very high condition number. Condition number of an eigenvalue is basically how fast eigenvalue can move under perturbation, right? So basically, the distance an eigenvalue can move under perturbation epsilon is basically equal to kappa, the condition number of my eigenvalue time epsilon. In those cases where you have this effect, condition number is exponentially large in system size. So now in this case, it would be for this, n500, it would be like, I don't know, I'm making up numbers, 10 to 500. And that's why you can sort of move very far away. Now, what I meant by spectrum amplification is perhaps I can make this comment in the context of this turbulence that I mentioned here, right? So if you have this non-Hermitian operator where pseudo spectrum is very much different than spectrum, this means that you have some almost eigenmodes. So those are points in the pseudo spectrum, right? You have almost eigenmodes that for short times can dominate your dynamics. And the behavior of this can be very much different. So in this sense, for instance, in this context of turbulence, so there are some almost eigenmodes that for finite but long stretch of time can destabilize your laminar flow. So if you have a linear operator which has very high condition number, then somehow you can be very sensitive to perturbations in some window of time. And then depending on how you take thermodynamic limit, this finite window of time can get actually infinite, and then this is the relevant physics actually. I don't know whether I fully answered, but yeah.
Yes, thank you, Marco. Shashi, feel free to follow up on that in the chat if there's more. Maybe one final question here, as actually time's moving pretty fast on us. Can you tell us about any connections, or have you thought much about the connections between this kind of work and the question of pre-thermalization, many-body localization, whether it exists or doesn't, and even more recently many-body resonances, which are another way of looking at this question?
Right. So yeah, one sort of immediate question that I also got from some people was whether this is like pre-thermalization, right? Because it kind of say in this case where the initial decay is slower, you relax slower initially.
Mm-hmm.
But still, I would say it's different than pre-thermalization, right? Because with here you are still relaxing exponentially. It's just that the rate is a bit smaller than you would expect. So in this sense, there is no like pre-thermalization. You could get effect which, I don't know, one might call pre-thermalization, like delayed thermalization, if this pseudo spectrum, this would be equal to 1, right? So that this phantom relaxation rate would actually be 1. And there are actually some situations, we are just writing up paper with my student Yash Bensa about such a case. So if you look at OTOC and brickwork circuit with periodic boundary conditions, then you can have a bit situations like that, where this lambda phantom actually can get up to 1. But this, I would say, it's like non-generic. So typically you expect it to be less than 1, and therefore you will not have this sort of arrested thermalization or pre-thermalization.
Excellent. Marco, thank you very much. Seeing as we're 10 minutes over here, maybe this is a great time. If you want to share any final words with us and the audience, this might be a good time.
Yeah, thank you, Zlatko, for invitation. And if people want to know more, they can just email me also. So happy to discuss.
Okay, wonderful. Well, Marco, it was a real pleasure to have you in the seminar today, folks. Thank you for all the questions and discussion. I see there are a lot of people sending nice words and thank you from Kevin and Shashi and others in the chat. With that, folks, this will stay recorded, so you can go back and rewatch it. But you can only tune in live every Friday at noon Eastern Time. So to know what's coming up, click like and subscribe, and we'll see you next Friday at noon Eastern. Take care.
Bye-bye.